Hello, this video is on logarithmic equations and is presented by the Oakton Community College Math Department. The objective of this video is to learn how to solve logarithmic equations. So we will be looking at the three types of logarithmic equations and working on techniques to allow us to solve them. There are several things that we do have to keep in mind as we work through this section. The first part we have to remember is the definition of the logarithm. So this states that log base b of x is equal to y, our logarithmic expression, can be rewritten into an equivalent exponential expression in one of two ways. We can either rewrite it simply by using definition, that log base b of x equals y is equivalent to x equals b to the y, or we can use what's known as the inverse property, which states that if you exponentiate a logarithmic a logarithmic expression at the same base as the base of the log, then all you're left with is the argument. So in symbols, b to the log base b of x is equal to x. We also have the three properties of the logs that allow us to manipulate logarithmic arguments and to simplify the logarithms. So our three properties are the product rule, which states that log base b of a product, m times n, becomes the sum of the logs. Log base b of m divided by n, so the quotient rule, states that the log of a quotient becomes the difference of the logs. And lastly, we have the power rule, that log base b of m raised to a power equals the power as the coefficients of the log, so p times log base b of m. Keeping these rules in mind, we can now tackle the three types of logarithmic equations. So the first type of equation I want to look at is an equation that simply has one logarithmic statement. So if we look at this equation, we want to solve for x, and as we scan through our equation, we see 6 times the natural log of 2x, but then we see constants, or number. So because we only have one logarithm, the very first thing we want to do is to get this logarithm by itself. In other words, we want to isolate the logarithm. All right, and so using algebraic steps, first thing I would do here is add 4 to both sides, and so I'm left with 6 times the natural log of 2x is equal to 30. Again, I want to get this natural log by itself, so I divide both sides by 6, and I'm left with the natural log of 2x. It is equal to 5. So we now have the logarithm by itself. We have isolated our logarithm. So how do we get rid of the log? The second step, once you have isolated your log, is to exponentiate both sides at the base. So I exponentiate both sides of my equation at the base of my logarithm. And so in this case, because I have a natural log, remember that the natural log is a way of writing, a shorthand way of writing log base e. So we'll never see log base e, but because my base is e, I exponentiate both sides at base e. So e becomes the big number to both sides. Natural log of 2x is on the left, 5 is on the right, and because these two statements, log base e and e, have the same base, they essentially cancel each other out. This is our inverse property. And so we are left with 2x is equal to e to the 5th. And so when we divide by 2 to get x by itself, we have x is equal to e to the 5th divided by 2. Now it's very important to remember that when you're working with logarithmic equations, you must check your solution. Keep in mind that the domain of the logarithm is all positive real numbers. And so because we have to make sure that our logarithm is defined, before I can just say this is my answer, I have to plug my x, whatever I think it is, back into all of the logarithms in my equation and check to make sure that they stay positive. So I would check here natural log of 2 times e to the 5th divided by 2, and this is natural log of e to the 5th. And I don't really have to work this out any further. I can see that this is going to be positive. But if you remember, log base e of e, these cancel each other out, and I have 5. And so that is a positive number. It works. And so this is our solution. So to review our steps, when you are working with equations that contain one log, to solve for x, first you isolate the logarithm, whatever it is, get that by itself, and then once you have the logarithm by itself, you exponentiate both sides at whatever the base of the logarithm is. And lastly, always remember, and we'll even say this is step 3, to check your answer. All right, and so if you want to practice this on your own, I suggest you look at these two equations. We have log base 5 of x minus 7 is equal to 2, and we have 6 plus 2 natural log of x is equal to 5. In both of these equations, there's exactly one log, and the rest are constants. And so you can follow the steps from above. Let's move now to the second type of logarithmic equation. These are equations that contain multiple logs, so you have more than one, and you have constants, you have numbers. So in this case, I want to solve for x, and I have log base 5 of x plus log base 5 of 4x minus 1 is equal to 1. Now, you may be very, very tempted to do the following, which is to just write 5s everywhere because it's base 5 and cancel, 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 right? No, we cannot do this because what you've done is illegally use the inverse property. The only time I can exponentiate both sides is if I have one log. As soon as you have multiple logs, so in this case I have 2, that means I have to do a different step. And the step I have to use here is to remember our properties from before. I have the sum of 2 logs. And so if I want to condense these logs into one log, remember that the sum becomes a product. And so I can rewrite this statement using my product rule as log base 5 of x times 4x minus 1 is equal to 1. So notice that what we did here is we get all logs onto one side, and then once you've done that, you use log properties to condense the logs. Okay, and so now what do we have left? We have a logarithm equation with one log and a number. And since the log is already by itself because we condensed it and because of the way we do this process, I look at my base. Now I can legally exponentiate both sides at my base. And so I have 5 to the log base 5. These essentially cancel each other out. So I have x times 4x minus 1 on this side, and 5 to the first power is 5. And so it's very important to remember to exponentiate both sides. And now we're left with a quadratic equation. So when solving a quadratic equation, I have a few steps here. First, I want to expand this, so I would distribute the x in. So we have 4x squared minus x is equal to 5. And then I always want to move all of my terms onto one side so I can set everything equal to 0. So we have 4x squared minus x minus 5 is equal to 0. At this point, I have two options. I can either use the quadratic formula, keeping in mind that a is 4, b is -1, and c is -5, or, which we're, in my opinion, lucky in this case, that this factors. So I have 4x and x because of the 4x squared. I have 5 and 1 because of the -5, and because it's negative, one's negative and one's positive. So when you check this, you have -5x plus 4x is -x. By the zero product property, I then set each of these terms equal to 0, and I get two possible answers. X is equal to 5/4 and x is equal to -1. And so before we start saying we have two answers and this is it, we have to remember to check our answers. So when I check my answer, I'll start with -1. I plug it into all the logs. So as soon as I start with the first one, log base 5 of -1, that's a red flag because I can't have a negative number inside my log. I cannot have a negative argument. Because of that red flag, because it didn't work in even just one of the logarithms, that means this is not a solution. So now when I check x equals 5/4, I have log base 5 of 5/4, positive, fine. I have log base 5 of 4 times 5/4 minus 1, which is log base 5 of 4. And pardon my writing is kind of degenerating here, but that's still positive, and so that means that this answer works, and x equals 5/4 is our only solution. If on an assessment, if on your class, if you wrote for your instructor that both of these were solutions, they would take points off, because x equals -1 is what is known as an extraneous solution. It does not work in the equation because it's not in the domain. All right, so to review the steps again, when you have multiple logs and you see even one constant, one number by itself, first, we want to get all the logs onto one side, which we already had here. Second, you want to use the log properties to condense the logs into one log, and then you solve it as we did in the logs with just one logarithm. For extra practice, you can try these problems. So you have log base 6 of x plus 3 plus log base 6 of x plus 4 is equal to 1. And you have log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. Notice that you'll be using two different properties in these two examples. Okay, and so the fun continues. We have our last set of equations. These are equations with multiple logarithms, so just like before, we don't have just one log, but on top of that, we have no constants. So there are no numbers by themselves. So in this equation, we want to solve for x with log of 3x minus 3 is equal to log of x plus 1 plus log of 4. There is no number, there's no constant by itself. Every term here, or if I can use term lightly, everything has a log here. So because everything has a log, there's one more property that we have to use, and that is the one-to-one property of logarithms. This states that for all appropriately defined x and y, log base b of x is equal to, and if, log base b of x is equal to log base b of y, then x is equal to y. So a shorthand way of saying this is very imprecise, but we can kind of get away with it. If you have the same base on both sides, one log on one side, one log on the other side, same base, the logs cancel, and all you have left are the arguments. So notice what we have in our equation above. We have log of 3x minus 3, and that's one log, but we don't have one log on the other side. We have log of x plus 1 plus log of 4. Because we have multiple logarithms, we should always have those properties in the back of our mind. And so if I use the product rule again here, because I have the sum of the logarithms, I can condense those two logarithms to log of 4 times x plus 1. And yes, I changed the order there. I'm just being a little finicky, excuse me. I like to write my numbers first. But if you wrote x plus 1 times 4, that would also be correct. And so now I have the perfect setup. Log with no number means it's log base 10 of 3x minus 3. Log, again, base 10 of 4x plus 1. Because of the one-to-one property, I can essentially cancel the logs, and I have 3x minus 3 is equal to 4 times x plus 1. And now I just solve this like a normal linear equation. So I have distributing the 4, 3x minus 3 is 4x plus 4. And then if I isolate the x, I have subtracting 3x from both sides, and I'll do two steps here, subtracting 4 from both sides, -7 is equal to x. And I think hopefully 3 problems in, we are accustomed to this by now. We immediately check our answer, and when I check -7 in log of, let's just grab log of x plus 1. If I plug in -7, I have log of -7 plus 1, which is equal to log of -6. That is a problem because I have a negative number inside the log. And so that means that this answer is eliminated and there are none left. So once again, if you wrote down that x equals -7 is a solution, that would be incorrect. There is no solution here, simply because -7 is not in the domain of this problem. And so no answer in the domain of this problem works. If you would like to do a practice problem, I only have one this time, I'm kind of cutting back. We have log of 5x plus 1 is equal to log of 2x plus 3 plus log 2. So keep in mind that multiple logs means keep the properties in the back of your head. You're looking for adding logs, subtracting logs, and coefficients. If you have one log, that you can exponentiate both sides of the base or rewrite it into its exponential form. And if you have constants versus non-constants, that's what separates the multiple logs. If you have any questions about this, I encourage you to talk to your instructors, and I wish you all a wonderful day.